Today we begin talking about what are called Taylor polynomials, named after the mathematician Brooke Taylor. It is a group of polynomials that are used to estimate a curve. Now, we have estimated curves before, and the method that we used last semester was called linearization. We tried to find the square root of, say, 123 without a calculator. We tried to estimate it. So what we did is we found the tangent line at 121, which we can find the square root of, and we used that tangent line to find the approximate square root of 123. Do you remember doing that? Vaguely. Okay. Now, a line is only good right at the point of tangency and really nearby. But what we're going to do today is we're going to expand on that. Instead of using lines, we're going to start using polynomials. And polynomials curve. What does a quadratic look like? Draw one in the air for me. What does a parabola look like?
A big U.
It's a big U. Touchdown. It's a big U. What is a cubic look like? Do you know? It kind of does a little S-y thing like a tangent line does. It can also make a big N, cursive N. Fourth powers, they actually look like W's sometimes. They're like a parabola, but they do a W thing in the middle. They can. Sometimes they look just like a parabola. But because they curve, they can fit other curves better. Now, Taylor polynomials were developed back in the day when they did not have access to the natural log of 5, or e to the third power, or the sine of 47 degrees. And these curves were created to mimic the other curves that they can't find values for so that they could find values close by. Okay? So what we're going to do is we're going to actually start halfway down this page, and we're going to look where it says, draw a line right above where it says as a preliminary. That's our starting point. Okay? I understand that you have been exposed to this thing called a factorial. Does that word sound familiar?
Yes.
Something you learn in pre-cal?
Yes.
Okay? And it is a variable or a number with an exclamation point on it. Okay? What does 3 factorial mean? 3 times 2 times 1. We usually say it backwards. 3 times 2 times 1. 10 factorial would be 10 times 9 times 8 times 7, blah, 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 all the way down to 1. Now, let me talk about where it is on the calculator because you may need access to it. So go ahead and take your calculator, please. I cleared mine out on purpose. Okay, we're going to find 10 factorial, just for fun. So type in a 10. And then after you've typed in 10, push the math key. And then I want you to left arrow to highlight the PRB. And that stands for probability. And notice that choice number 4 is the factorial. So you choose 4. There's 10 factorial, which is 10 times 9 times 8 times 7 times 6, and all the way down to 1, which is a rather big number. 3,628,800. Okay? So, factorial is going to show up again later today. And so now you have access to where it is. And I'm glad you guys already know what it is. All right? So, we're going to go to the next paragraph, which says we start this section by trying to find a polynomial function p that approximates a function f. For instance, let f of x equal 16 square root of x. We're going to start right there. Take your calculator, please. Go to y equals and type in 16 square root of x. Okay, you can't see what I'm doing, so we're going to move it over there. 16 square root of x. Now, on your paper at the bottom, there is a grid. Do you see that graph right there? We're going to set our window basically the way that one is. So push the window key. Let's go 0 to 4 on the x. And then 0 to 30 on the y. That'll be fine. Or 0 to 40 is what I did last class. That's right. And then scale of 10 on the y, since we're going to 40. Okay? After you've set those parameters, please press graph. Don't press zoom anything because you're going to reset everything. Press graph. And there you have 16 square roots of x. All right? Now, that is our first curve, and I'm going to go ahead and underline it. I forgot to do that before. Now, the second curve we're going to put in is this long p of x equation right there. It is called it's a polynomial. It's a funny looking polynomial. We really haven't written them that way before. But this is a polynomial that has the same y value as my curve I already have at 1. And then, because of the way it's constructed, is almost exactly the same as the square root graph all the way around 1. So go back to y equals, go to y2 and type that one in. So parentheses, x minus 1 to the third minus 2x minus 1 squared plus 8x minus 1 plus 16. And just push graph when you're done. These two graphs really like each other, don't they? They really like each other. They're very close for quite a bit of the graph, as opposed to a line which would just touch it in one point. Are you following what I'm saying? Mm-hmm. Okay. What I want you to do now, yes?
Is it okay if I see the last number on the equation?
16. Okay. Now what I'd like you to do is push the trace key, which is on the top row, second from the right, and push 1, and push enter. That is the exact place where they touch each other. Now it looks like they touch each other for many, many points, but they don't. They're just really, really close. All right? So those two are pretty close to each other as far as 1 is concerned. They're also close probably all the way out to here and all the way out to here. So all those values on the polynomial are just as good as the values on the square root graph. Okay? So let's do one more thing. I want you to push second and window. Everybody push second and window. We are going to change the calculator into ask mode. We haven't done this since limits, I don't believe. So down arrow to where independent says ask, and push enter to make it ask be highlighted. Okay? And now go to the table, which is second and graph. You're going to need it here for your homework. So we're just going to leave it like this. Now, they touch at 1. So type in 1. And notice that both y values are the same. Do you see that? Now let's push a number that's kind of far away from 1, like 0.5. That's quite a ways away. So 0.5, look how close they are. 11.314 versus 11.375. That's a pretty close estimate, okay? Let's go the other side. Push 1.5. What do you see? 19.596 versus 19.625. They're only off by 0.029, okay? So they're pretty close as well. So the point is, well, why in the heck would you want this long, nasty equation in place of this equation? Well, because back in the days before calculators, they couldn't figure out the square root of 1.2. But plugging 1.2 in here and doing the math only involves adding, subtracting, and multiplying. And you can do that by hand. Okay? So back in the day, these polynomials were very, very helpful in figuring values on these curves that they couldn't figure out. Today we use them and they have much more significance in upper level college mathematics, but we need to understand them now and how they're constructed. Okay? Now the question is, where in the heck did they come up with this equation? That's what you're going to learn how to do today, is how to build these. For each one is built specifically for the graph it is going to touch and where. All right? Any questions to this point? Nope? All right, turn the page, please. The top of the next page starts talking about how we do this. What do we do? And it's a little bit confusing at first, but once you get the hang of it, it's pretty easy because it's a lot of patterns. All right, let's see here. It says to find a polynomial function p that approximates a function f, we begin by choosing some number c such that the value of f and p are the same. That is, f of c equals p of c. Who can tell me in simple English what that means, f of c equals p of c?
The
The y values are the same at c. So basically, that's the point where the two graphs are going to touch each other. Okay? So you got to pick a point where you want that to happen. Okay? So, in addition, the derivatives of the two functions must be the same. The derivatives of the two functions must be the same as well. That is that f prime of c is got to equal p prime of c. So we want them to have the same point, and then we want them to have the same slope. And that's how we did linearization anyway. We did linearization the same way. If that is true, we say that approximating polynomial is either expanded about or centered at c. Centered at c is used more commonly. So whenever you see a homework problem, they're going to say build a 5th degree Taylor polynomial centered at 5. Well, that tells you that c is 5. Okay? So that's the verbiage you need to be looking for. Now what we're going to do is we're going to build a 1st degree polynomial, a linearization, just to see and review what the process is. With these two requirements in place, we obtain an approximation of f using a 1st degree polynomial function, in other words, a line. For the function e to the x, which is a nice easy one to do, find a 1st degree polynomial function p of x, which is written in this format. It is a sub 1x plus a sub 0, whose values and slopes agree with the value of the slope of x at x equals 0. And then he wrote in, Master Math Mentor wrote in, he said, I know you're not wild about the coefficients a1 and a0, but they're necessary, okay? So just bear with me. a1 is like the slope, and a0 is the y-intercept, agree? That's where they are. Okay? Now, we're using e to the x is our function, and x equals 0 is the point that it is centered at. So if the equation of the polynomial we search is this p of x, we must first impose the condition that p of 0 equals f of 0. That will allow us to solve for the a of 0. So I'm going to write underneath here p of 0 equals f of 0, and I'm going to actually find out what number that is. Okay, I know what f is already. If f of 0 is e to the 0, what is e to the 0? 1. So p of 0 and f of 0 are both 1. So what that means is I'm plugging the point 0, 1 into my polynomial function. So p of x is like the y, so we write 1 equals a1 times 0 plus a0. 0 for x, 1 for y. So what cancels out? A1, 0. So 1 is equal to a0. So I now know that the a0 term, the last term, is a 1. If the slope of the polynomial p must equal the slope of the function also, that will allow us to solve for a1. So I'm going to write this down. P prime of 0 equals f prime of 0. And what does that equal? Well, look back at f of x. It's up here. What's the derivative of this function? E to the x. And if I plug in a 0 to the derivative, what do I get?
0.
I get 1 again, don't I? Because it's the same function, right? So this is also equal to 1. So this means I'm plugging 1 into the derivative. So go back to your p equation here, take its derivative. Remember that a's are constants. So p prime of x is equal to, what's the derivative of a1x? A1. And what's the derivative of a0? 0, because it's a constant. And we're supposed to set this derivative equal to 1, aren't we? Is there any solving to do? No. So I'm done. A1 also equals 1. So now we know that a1 and a0 are both 1s. We can write our linearization in this new way. P of x equals 1x plus 1. Okay, so in the next paragraph it says, so the 1st degree approximation for e to the x at x equals 0 is p1 of x. Usually we put a subscript on our p to tell which degree we're doing, equals x plus 1. if you look at the graph right next to that, there is a picture of e to the x next to the line we just created, okay? Now, if I needed to approximate something very, very, very close to 0, I'd be good. But anything farther away than, say, 0.3 or 0.4, way off, especially if I need accuracy. So a line's all right, but it's not the best. So what would make a better approximation besides a line? A parabola. Parabola would be better, wouldn't it? Because that's curvy. Wouldn't we want something that was kind of curvy and then hugged against it better? Mm-hmm. Yes. So what we're going to do now, to improve this approximation, we now use a quadratic as our polynomial. And we further require that the values of the second derivative agree at 0. Okay? The values of the second derivative have to be the same. Okay. The function tells us y values on a graph. The derivative tells us slope on a graph. What does the second derivative tell us? Concavity. So we want both of our curves to have the same concavity at the point of tangency. We don't want one to be concave up and the other one to be concave down. That wouldn't help, would it? No. Okay. So here is our new polynomial that's quadratic. Has an a2 in it now. a2x squared plus a1x plus a0. So it's the same one we had before, but we just threw another term in the front. Do you see that? Mm-hmm. Okay. Our function is still e to the x. Now we need to find a0, a1, and a2. So I'm going to make things a little simpler on myself. I'm going to say p of 0 is equal to p prime of 0. We already figured that out. Is that also going to equal p double prime of 0?
No.
What's the second derivative of e to the x? E to the x. When you plug in a 0, are you going to get the same answer you've gotten all along? Yeah. Yes. So this equals p double prime of 0, which equals 1. So every time we build our new derivative, we always set it equal to 1. Okay? So we start with p of 0 equals f of 0. So we take this original equation, we're going to plug 0, 1 into it again. So 1 equals a2 times 0 squared plus a1 times 0 plus a0. 0 for x, 1 for y. So now a2 goes away, a1 goes away, and a0 is 1. Now p primes, the derivative. We're still going to plug in 0, 1 because it's always 1, but now I need to take the derivative of this thing. So carefully do this. P prime of x is equal to, now let's just forget about the subscript of the 2. If this is ax squared, and a is a constant, what's the derivative? 2ax. So 2a sub 2 of x plus, what's the derivative of the next term? a1x. Just a1. And we're supposed to set it equal to 1 again. Oh, we got to plug in the zeros. Forgot to do that. Or can you do that in your head? Mm-hmm. Yeah. So what does that tell us? a1 is equal to 1. Now the question is, do you think that the fact that a0 and a1 are the same numbers they were in the previous problem is a coincidence, or is it supposed to happen that way? It's supposed to happen that way. You are right. So you don't, if they ask you to build a 5th degree, you don't have to build 1, then 2, then 3, then 4. You can jump right to the 5th one. You don't have to do them in this sequence. Well, we're looking for the patterns is what we're doing. Okay? So now 0, 1, again, we want the second derivative. I'll tell you what though, a2 is not 1 again. So the second derivative of this function would be just 2a2. The x falls off. And we're supposed to set that equal to 1. So now a2 is 1/2. Okay, so now we can write our formula, taking those a's out and putting the numbers in. So p of x is going to be 1/2 x squared plus 1x plus 1. So there's our quadratic. There's our parabola that fits e to the x best at 0. Okay, now there's a picture of it at the bottom. They already found it. Is that a better fit? Is that parabola a better fit to the polynomial at that point of tangency? Definitely, it's better. Okay? So, now, turn the page. What would be even better? Well, if we did a third degree, a cubic. But we're not going to do all the math. I'm just going to give you the answers. Well, we don't even have to do all the math because we know what A0, A1, and A2 are going to be, don't we? Okay, so turn it over. Here we go. So, we know that A0 is going to be what? What did we find? 1. A1 is going to be 1 again. A2 is going to be 1/2. And I'm just going to tell you what A3 is. What do you think it, probably you would think 1/3, right? But it's not. It's 1/6. 1/6. Well, why is it 1/6? Okay, watch this. If you take a cubic and you take its derivative until it becomes constant, what's going to happen? You're going to get 3x squared, right? And then the 2 comes down, and that's going to be 6x, and then it comes down to 6. So the denominator becomes a 6. Okay? Now, here's the thing. What would the denominator be for the next one? If I did excuse me, let me be more specific. If I did x to the 4th, what would the denominator be?
0. 24.
It would be 4x to the 3rd, 12x squared, 24x, 24. So, if I went farther, it would be 24. Well, what's the significance of this? Well, this denominator happens to be 2 times 1. This denominator happens to be 3 times 2 times 1.
Oh.
The next denominator happens to be 4 times 3 times 2 times 1. And you see why? Because you started with a power of 4, you brought it down, became a power of 3. Then you brought that power down, became a power of 2, brought that power down, so you're creating a factorial in front of your number. So this is one of the places that factorials show up, and that's why we talked about it at the beginning of class. Okay? So here's the third degree, 1/6 x to the 3rd, 1/2 x squared, x plus 1, and it fits even better than the quadratic did. It's much better. All right, now, if we went on and on and on and on and on, we would discover that this is the pattern right here for e to the x only. E to the x is a great one to do. It's 1 plus x. Now this x right here, I'm even going to tell you, they just kind of leave it out. This is 1 over 1 factorial. And then the next one is 1 over 2 factorial x squared, 1 over 3 factorial x to the 3rd, 1 over 4 factorial x to the 4th, blah, 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 blah. So if you happen to memorize this one, because it's so common, and we're going to put it in our new flip charts that we're going to make starting next week, you memorize this one. If they ever ask you for a 5th degree Taylor polynomial for e to the x, you don't have to do all the math. You can just write it down. Okay? So that's how these work. They follow patterns. So please go to the bottom of this page, put a big star by this box, because this is like big deal. These are your formulas. Okay? In the previous example, when we did e to the x, we centered at 0. We want to talk about what the pattern is if we center elsewhere. Okay? So, a nth degree Taylor polynomial centered at c looks like this. You start out with f of c, then you do f prime of c, and if you want to put this over 1 factorial, you can, x minus c, and then f double prime of c over 2 factorial, x minus c squared, and then it keeps going. So do you see how this factorial and this power are the same?
Yes.
Next term, same thing. This power, that factorial, this power is the same. Also, whichever derivative it is the same. Okay? So the next one would be the 4th derivative over 4 factorial x minus c to the fourth. And then it goes out however far it tells you to go. Okay? In hand-done mathematics, we usually go out 4 or 5 max. Computers can go out to 20, 30 and get even better estimates than anything else. Okay? Now, if c is 0, if you're centered at 0, it's actually called an nth degree Maclaurin. That's how you pronounce that. Maclaurin. Yes?
I was just wondering, why is the factorial on the bottom of the fraction again?
Because when you take the derivatives of the powers, the power always goes down to the front, and then it drops 1. So when you take the derivative again, you have that number and the number right after it, or before it, every time. It's going to always work. Whenever you take derivatives, you're multiplying the front number by the power, and then 1 less, and then 1 less, and 1 less, and that's what makes factorial. Okay? So Maclaurin polynomials are centered at 0. So they sometimes will throw that word at you and say, generate a Maclaurin polynomial. You automatically know to use just x's. Notice there's no x minus c, because there is no, c is 0. It's just a simpler way to do it. So these are a subset of these. Maclaurins are a subset of the Taylors. Okay? Now, we're going to go ahead and do this with a different function. Okay? And I'm going to show you the best way to organize it and make it not so difficult to work through. We're going to also find that there's 4 different functions that these work really well with. E to the x is 1, ln is another, sine is the third, and cosine is the fourth. And those, we're going to develop all of those within this class today. Okay? Here we go. Next part. All right, now we go to the next page. And we're going to do number 2. It says find the Taylor polynomials P1, P2, P3, and P4 for f of x equals ln of x minus 1 centered at 2 and complete the table. Now, once we find P1, we just get to copy it for P2 and get to copy that for P3 and so on. So it's not going to take as long. All right, so here we go. We have the function, and we're centering at 2. So that means we have to plug in 2 to the function and each of the derivatives after that. So when you plug a 2 into here, what do you get? You get ln of 1, which is what? 0. So put a 0 right there in that box. All right, now I'm going to grab something real quick here that I'm going to need in a minute because you don't have room to show all the steps for the derivatives. I'll get that in a second. What is the first derivative of this? This is pretty quick. You can do it in your head. What's the derivative of ln of x minus 1? 1 over x minus 1. We're going to just do all the derivatives at once. Just get them done. Okay? So, if I'm going to take the derivative again, I have 2 options. I can do Lodi high, or I can bring this up and rewrite it to the -1 power. That's faster. Okay? So when I take the derivative of this, what do I get? -1.
Parentheses x minus 1.
X minus 1 to the
Negative,
-2, but I want to write it as a fraction over here, so this would be -1 on top, and then x minus 1 squared on the bottom. Agreed?
Mm-hmm.
So that's what goes in the box, -1 over x minus 1 squared. Okay? Now to take the derivative again, I'd rather not use the fraction form. I'd rather use the negative exponent form. So what would it be? Not -2, careful. Positive 2,
2 over x minus 1.
x minus 1 to the -3, agreed?
Mm-hmm.
So that would be 2 on top, and then x minus 1 cubed on the bottom. Now if you could do the whole thing in your head carefully, feel free to do so, but I'm just going to look at this over here. So what's the numerator going to be? -6, x minus 1 to the 4th, agreed? So there are my derivatives. In order to use the formula, I have to plug 2 into all of those, because those are going to be the numerators of my coefficients on the x's. Okay, so I need to pull this off. If I plug 2 into this derivative, what do I get? 1 over 1, which is 1. Agreed? This one will be -1 over 1 squared, which is -1. This one would be 2 over 1 to the 3rd, which is 2. And this one would be -6. Okay? So now we're ready to start building. The P1x is going to be, you start with the y value, which is 0, plus the first over 1 factorial times, we're centering at 2, x minus 2, to the first. Everything's ones on the first term. I'm writing out more than I really need to, just to show you how the pattern goes. It's the one I got in the box in front of it, over 1 factorial, because it's the first derivative, and then x minus 2 to the first power. That's it. Okay? So now, I'm going to clean it up a little bit to do the second one. Now remember, with the second one, you just bring it straight down. So 0 plus 1 times x minus 2 plus, now the formula, which I'm going to bring back up here for you to see. I'm doing this from memory because I just did it last period, but it's brand new to you. We're using this Taylor polynomial. Okay, it's the second derivative at c, which is these numbers in this column, is the numerator, and 2 factorial is the denominator. Can you see what I'm pointing at up here, or is it off the screen? Yeah. You can see it. Okay. So that means it's going to be the negative 1 on top, 2 factorial on the bottom, and then x minus my c, which is 2, squared. Are you with me? Okay. For the third, we're going to just copy down everything. 0 plus 1, x minus 2. And every time we do a step, let's just clean up the coefficient in the front, because they make a pattern. So what is 2 factorial? 2 times 1, which is just 2. So this is negative 1/2, x minus 2 squared. Now we got to add another term. So we put a fraction. What's going to go on the bottom? 3 factorial. And out to the side is x minus 2 to the third. Those are all those 3's. And the top is this number I wrote right here. So 2 goes on top. So that line's done. Okay? Now we do the fourth one. So 0 plus 1 x minus 2 plus negative 1/2 x minus 2 squared plus, what is 3 factorial? 6. So what is 2 over 6 reduced to? 1/3. 1/3 x minus 2 to the third plus, okay, remember that this is the top number. The factorial, which factorial are we up to now? 4. 4 factorial goes on the bottom, and the 4 is also the power on my x. X minus 2 to the fourth. Okay? Now, I'm going to skip the simplifying box because we've been simplifying all along, except for this last one here. So what is the last term going to be? It's going to be plus, what is 4 factorial? 4 times 3 times 2 times 1 is 24. So negative 6 over 4 factorial reduces to negative 1 over 4. X minus 2 to the fourth. And what was the term in front of it? 1 over 3, x minus 2 to the third. What was the term in front of that? Negative 1 over 2, x minus 2 squared. Coincidence? No. It's a pattern. Okay? Now, do you think you could figure out, without doing all the math, what would the fifth term be? I don't even have to take the derivative. What's the numerator every time when I clean it up?
The number of the
Okay, it's the number plugged in, but notice that it changed to 1, then negative 1, then 1, then negative 1. So what's my next numerator going to be? 1 over 5, because I just did 1 over 4, right? X minus 2 to the fifth. So it's everything in front of it, and now with that added on. Okay? So then the sixth one would be all of this plus, it's going to be negative, because notice they were flipping signs, right? They'd alternate positive, negative. Negative 1 over 6, x minus 2 to the 6. We're done. Okay? So LNs make this pattern. Yes, ma'am?
Where did x minus 2 come from again?
Okay, the Taylor polynomial formula says that you put x minus c next to every one, and c is 2. Okay? It's the point where we are touching. The two graphs are touching each other. Is at 2. So we have to put it as part of the formula. Okay? So do you see how this one builds itself? Once you've done a few terms, the rest of them start just kind of falling into place. It's a lot of patterns in this chapter. Okay? Now, I'm not going to go through graphing all of these things to show how they work. We're going to jump over and we're going to derive sine and cosine. So turn this packet to the next page, top of the next page. Okay, I'm going to do sine with you, and then I'm going to have you do cosine and see what happens, okay? So it says find the Maclaurin polynomials. Now, what does Maclaurin mean again? Do you remember? It says that c is equal to, take a look, go back and look at your notes. Where is the Maclaurin? It's the bottom of the previous page on the front. If c is centered at 0, bottom of page 79. Okay, Maclaurins do not have x minus c, they just have x's, just plain x's. It makes life easier. So it's just the number over 2 factorial, the number over 3 factorial, the number over n factorial, and so on, okay? So that's what Maclaurin does. So c is 0. That's why they have zeros all along here. They're plugging in 0 every time, okay? So now, we're going to fill in this row. It's going to go very quickly. F of x, you put the function right here. So please write sine of x in the first box. And now we're going to take the derivative multiple times because it loops. It's not too long. What's the derivative of sine?
Cosine.
Cosine, right in the next box. What's the derivative of that?
Negative sine. Negative sine.
Negative sine. And then what's the derivative of that?
Negative cosine.
Negative cosine. And then positive sine. And then it repeats, doesn't it? We're back to where we started. So cosine comes next. And then negative sine. And then negative cosine. Okay? Yeah, it didn't take long. If all derivatives were just that easy, right? Okay. Now we're going to plug in 0 to each one of these. These are going to be our numerators. So what is the sign of 0? 0. Put a 0 right there. Cosine of 0 is 1. Negative sine of 0, 0 again. Negative cosine of 0, negative 1. Sine of 0 is 0, cosine of 0 is 1, 0, negative 1. Since the function's repeated, their answer's repeated, right? Okay. Now, remember that these are the numerators. These are the numerators right there. The bottoms are the number factorial of what derivative you just took. Okay? So what is going to happen with the terms that have 0 as the numerator? It's going to be totally gone. It's going to be 0 over a number times an x, which is gone. Okay? So anytime you come across a 0, you skip it. You don't have to write it down. Okay? So when we do P1, it's just going to be 1 over 1 factorial x to the first, because that's the first derivative. And then 3 is going to be up through the third derivative. That's why they wrote P3, because we don't write down P2, because P2 doesn't even exist. The P2 term is gone. So this is going to be 1x, and then we go to the third derivative, so that would be plus negative 1 over 3 factorial x to the third. Remember that the numbers on the bottom row are the numerators. The factorial goes on the bottom, and it happens to be the derivative that you have taken. I took the third derivative. It's a P3, so 3 factorial goes on the bottom. Okay? So P5 would be the 1x again. And I'm going to go ahead and leave this as 1 over 3 factorial because there's nothing to reduce it with. X to the third. Now when we go to the fifth one, it's a positive 1 over what? What factorial is going on the bottom? 5, exactly. And then x to the fifth power. We're done with that one. Okay? So now we're ready to go to the next one. So it's going to be, under a little squiggle there, 1x minus 1 over 3 factorial x to the third plus 1 over 5 factorial x to the 5th. And you could actually probably get the last term without even looking at the data above. It's going to be plus or minus?
Minus?
It's going to be minus because the signs are alternating. 1 over 7 factorial x to the 7th. Agreed? I'm on the 7th degree. So it's 7 factorial x to the 7th. So notice that sine turns into a Taylor polynomial only with odd exponents. Okay? Questions? All right. Let's look at the cosine one. I'm going to get this first row with you to make sure we all match, and then you're going to do the rest. So f of x is cosine, so put cosine in the first box. What's the derivative of that?
Negative sine.
Negative sine. And then derivative of that is negative cosine. And then positive sine. And then cosine. And now we start repeating. Negative sine, negative cosine. Okay, you do the rest. Build the four polynomials. I forgot to say this in this class. I did it in the other class, but I'm going to show you it here. If you want to, under these numbers, you could write, this is 0 factorial, this is 1 factorial, this is 2 factorial. And that way you can see immediately what your denominators are going to be. Just start at the left, and whatever derivative it is, write 2 factorial underneath, and here are your fractions right there that you can write them down. If you're having trouble coming up with the fractions, this is a way that it could help you. There's a fraction, there's a fraction, and there's a fraction. So p sub 0 is just 1 over 0 factorial. That's just a 1. That's it. P sub 0 is 1. P2 would be that one minus 1 over 2 factorial x squared. Are we good there? And then,
How did you know to start with 1 minus instead of like?
because the numerator was negative 1.
Oh.
That's how I knew was to put the minus sign. So then 1 minus 1 over 2 factorial x squared, and the next term is plus 1 over 4 factorial x to the 4th. So now we copy 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4th. And then the next numerator is negative, so minus 1 over 6 factorial x to the 6th. And that one's done. All right. That's all we're going to do today as far as notes go. What I would like to do is do one of the homework problems with you. So let's go to the first one. So we're going to do it all at one time. First thing I need to tell you, listen carefully, we're going to omit 5 and 6. So mark out 5 and 6. And you're going to do all the rest through 10. Okay? Omit 5 and 6. So you're going to do 4 Maclaurens and 4 Taylors. Okay? So start with number 1. Find the Maclaurin polynomial of degree n for the given function and evaluate it at point 1. So here's what we're going to do. We're going to basically build a chart just like the sine and cosine chart we just did. We're going to have, we need to go out to the 5th derivative. So we're going to have f of x, f prime of x, f double prime of x, f triple prime of x. And now we really haven't talked about this. How do you write anything beyond that? You would think of you could do it with the d4x over dt squared or whatever, but there's another way. You can do it with this notation, but you got to be careful. The 4 cannot be written as just a 4 because it looks like a 4th power. What you have to do is you have to write it as an f with a 4 in a parentheses to the x. That means 4th derivative. If the 4 was out of the parentheses, that would mean 4th power. Okay, and then f parentheses 5 and then the x. So that's how you do derivatives beyond 3. So underneath here, I'm going to be colorful. First of all, under f of x, copy down the function, e to the negative x. Now we need to take its derivative 5 times. So the derivative of this would be negative e to the negative x. Agreed? What about the second derivative? Back to the e to the negative x. This is definitely cyclic, so negative e to the negative x, e to the negative x, negative e to the negative x. Because it is Maclaurin, what are we plugging in for x?
0.
0. Whenever it's Maclaurin, you plug in 0 for x. So on the next line, I'm going to go ahead and just draw a line right here. So 0 is getting plugged into all of these. When I plug 0 into the first function, what do I get? 1. Careful, in the second function you're going to get negative 1. In the third function, in the next function is going to be positive 1 again, then negative 1, then positive 1, then negative 1. Okay? Okay. If you want to, but you don't have to, and I'm going to do this just because I know some people are going to find it very helpful. I'm going to go ahead and draw fraction bars for each of these, and I'm going to put their factorials underneath them. Okay? So this first one, because it's no derivative at all, it gets 0 factorial underneath it. And then 1 factorial, 2 factorial, and double check yourself because the second derivative should be 2 factorial, 3 factorial, 4 factorial, and 5 factorial. Okay, now I have my coefficients. So all I need to do now is put them into the function. So P5 of x equals. Now we're ready to build. How many x's it gets is the factorial number. So 0 factorial is 1. So 1 over 1 is just 1. So this, because it's got a 0 on the bottom, gets no x's. Okay? And then the next one is negative 1 over 1 factorial, which is just negative 1. It is a first derivative. It's a 1 on the bottom, so it gets 1x. Plus, go ahead and leave this as 2 factorial. And its x is how many?
2.
Squared, because the bottom is 2 factorial. And then the next one is negative 1 over 3 factorial, x to the third, plus 1 over 4 factorial, x to the fourth, minus 1 over 5 factorial, x to the fifth. And if you go look on the back of this paper, on the second page, you will see that that is the polynomial answer. Now they want to know what an approximation to f of 0.1 is. So P5 of 0.1 equals. So what that means is now that we've built our function, we're going to go ahead and put it into y equals and plug in 0.1 and see what it's going to make. We're going to actually plug it in through the table. So take your calculator, go to y equals, and clear out the functions that are there. Now, it's going to be a lot more button pushings if you put in 2 factorial, 3 factorial, 4 factorial. If you can convert them in your head to what the numbers are, that's even faster. But if you want to put the factorials, you can. Doesn't matter. So it's 1 minus x plus 1/2, which is 0.5 x squared. Now the next one is 1 over 6. So I'm going to put the fraction bar, alpha y equals, and enter. 1 over 6 x to the third plus 1 over, now how do you get the next one? It's easy. Just take and multiply the previous denominator by the factorial number. So 6 times 4 is 24. X to the fourth minus another fraction bar, 1 over 24 times 5. You could actually type 24 times 5 on the bottom if you wanted to. And then x to the fifth. We're not going to graph it. We're going to go to the table. As soon as you're done, push second table, please. Second window. Or no, excuse me, second graph. Okay. Second graph. Push delete for the stuff that's there. Just delete, delete, delete. Clears it out. And we want to plug in 0.1 every time. So we're going to plug it in now, and then the next time we do a problem, it's already going to be there. We don't have to do any math. So we get, now if you will, notice it rounds it to 5 decimal places because that's all that will fit in the column. But if you go sit on top of it, you get all the decimals at the bottom. And for this lesson, more decimals is better. So I'm going to go out 6. 0.904837, blah, 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 blah. Okay? Now, just for kicks, the homework doesn't tell you to do it. I want to see how close that is to the real value of the function at that point. So the real function is e to the negative x, excuse me. Okay? So I'm going to go back to the home screen, and I'm going to type in e to the negative 0.1, because that's what I plugged in, right? How close is that to what I just got?
That's a real.
It matches exactly to 6 decimal places. And the next decimal was 4. I remember that. Let me go back to I want to go back to the table and see. 416. The 9th decimal place is where it starts diverting. Wow. Pretty darn close. And you're calculating these values this way. You know what? Taylor polynomials is how the calculator finds e to the negative 0.1. It uses a very long Taylor polynomial. I don't know how many iterations it goes, like a 15 or 20th degree Taylor polynomial, plugs in 0.1, and that's how it gets that value. Okay? That's how the calculator does it. Yes?
So do we know what the actual value is?
Yeah. Because it converges to the actual value. The Taylor polynomial converges to the actual value. So that's how we know it's right. Now, whoever Napier, who made all the log tables, would tell you that it works that way too. When computers go out to, 100th degree Taylor polynomials, it's gonna take millions of decimals to get them off, and that's how you know that they're pretty much the same thing. Okay? Any questions?